Okay, we just finished our screencast and we got to answer the question of the alternative way of finding the I through the bulb. I call that IB now, a little different than in the screencast or in the Zoom meeting we just did. I'll call this IM for the I microwave, and I'll call this I toaster. They ask for the I bulb, but you need to be able to find out if they ask for microwave or toaster, how would you find the current in those branches as well? I know this I total, I'll just call it I. The I coming into junction A is got to add up to the three currents leaving that junction. So IB plus IM plus IT has to add up. All right, because of the junction rule, because whatever charge comes into junction A, the same charge has to leave junction A. All right. The easiest way to find the current is the way we did it on the screencast, because I know, let's just call this junction B. I'll call this guy junction C, this guy junction D, E, and F. The easiest way is to figure out the potential difference across the bulb, which is delta V A to B, and divide it by the resistance of the bulb. The thing you don't know initially is what the potential difference is across there, but knowing that we've already solved for the current, that I was equal to, I think, 16.8 amps. I think that's what it was. I can't remember if it was 16.2 or 16.8. Let's say it was 16.8 amps. I can find the delta V across this resistor. I'll call it from, what are we at, G to H. The loss from delta V, G to H, is equal to the current, 16.8 times 1 ohm is 16.8 volts. So of the 120 volts, if you remember, as you were measuring the circuit with the light bulbs in it with the two leads on the voltmeter, if you measured the difference across that 1 ohm resistor, you would have a 16.8 volt difference. So of the 120 volts, you've got 103.2 volts left at point A. So the voltage at point A is 103.2, and that's true for C and for E. They're all at the same potential. So there's 103.2 volts there, and there's 0 volts at all these points. How do I know that? Because I know this is at 0 and this is at 120, right across the battery, and there's nothing between the battery's negative terminal and point B but bare wire. And that is a perfect wire with no resistance, so I don't have any energy loss across that. So these are all at the same potential. Same reason why A, C, and E are all at 103.2. So I could find the current IM and IT. I could just do IM is equal to 103.2 over 16, whatever that comes out to be, and IT would be 103.2 over 20, okay? And I'd get answers for both of those, and that's how much the current goes through those two. And you can see the current through the toaster and the bulb is exactly the same because they both are 20 ohm resistors. There's another way to do this, and that's what I alluded to at the end of our Zoom meeting today, and that's like the proportional method. But first, before I can do the proportional method, I have to reduce the two options for the current to go through. I have to reduce it to just two paths. So I have to combine the toaster and the microwave into a single resistor, into an equivalent resistor across the two of those. So what I'm going to do is I'm going to say the R equivalent for those two, for the toaster and the microwave, is 1/16 plus 1/20. And I'll do that on my calculator. And that comes out to be 8.9 ohms. Okay, so now here's how we proceed. It's as if, let me go to the next page. It's as if we had a new circuit that had the 1 ohm from the wire, the 20 ohms from the bulb, and then I've combined these two into the microwave and the toaster into a single resistor of 8.9 ohms. All right, so I've got this 16.8 coming in here. So this is I equals 16.8 amps. And some of it's going to go this way and some of it's going to go this way. Okay, of that 16.8, how much is going to go across the 20 ohm resistor and how much is going to go across the 8.9 ohms? So to figure that out, I'm going to label this, let's call this I2, let's call this I1. So we have to figure out how much current is going through each of those two branches. Notice that there's less equivalent resistance over here in the branch that I just simplified than there is in the bulb by itself. So I2 has got to be greater than I1. I2 is for sure going to be greater than I1. And it's going to be greater by the ratio of how much less 8.9 ohms is than 20 ohms in comparison with the total amount of resistance between the two branches. Here's what I mean by that. I'm going to add the 20 ohms plus the 8.9 ohms, and I'm going to get 28.9 ohms of resistance. Now, they're not in series. I'm not saying this is the equivalent resistance. So don't mistake what I just did for finding equivalent resistance. All I'm doing is finding the choice that the current coming in here into this node, it's going to go either down I1 or I2. More of the current's going through I2 because there's less equivalent resistance in that branch. I'm going to take the total current coming in of 16.8 amps. All right, I'm going to take that current, and let's say I want to solve for the bulb. So IB, I'm going to take that total current of 16.8, and I'm going to multiply it by the amount of resistance in the opposite leg, 8.9, divided by the total resistance of the two sides added together. So this is the resistance in the opposite branch, and that's the resistance across both branches. So you notice that I have a ratio, and this is 8.9 over 28.9. So the amount of current that's going through that portion, so it's 16.8 times 0.308, or 5.2 amps, just like it was before, just found it a different way. But now I can find out what I2 is by applying, I should have called this I1, not iBulb. I2 is that 16.8 times 20 over 28.9, because 20 is the amount of resistance in the opposite branch to the I2, and that's going to be obviously 0.692, because it's got to add up to 100%, and that is 11.6. But that 11.6 that comes out of here now is going to be split two ways again. So I've just found this current right here, 11.6 amps, and now I can use that same approach to figure out how much current goes through the toaster and the microwave. So I would take that 11.6 times 20 over 36. That would give me the amount of current in that branch right there, and the 11.6 times 16 over 36, that would be the amount of current going through the toaster. Notice how I'm going to have more in the microwave oven than in the toaster, which makes sense because the microwave oven has less resistance. So this 11.6 amps of current will be split two ways, with more going through the microwave oven and less through the toaster because of the resistances in those two branches. I hope that helps you with that way of solving for current in branches. Now let's talk about light bulb brightness. Okay, so let's talk about one of your mastering physics questions for tonight. It's I think this is the third one, and it says two light bulbs use different amounts of power. One uses 30 watts. We'll say P1 is 30 watts, and the other one, P2, is 60 watts of power when they're connected in parallel to a 120 volt source. So I'm going to show that in a little diagram here. Light bulbs in parallel would look like this. Get that little curly Q there. So let's say this is my 120 volts. And I'm going to call this my P1 and this is my P2. Actually, let me rename those. Bulb 1 and bulb 2. Bulb 1 is the 30 watt bulb, all right? So clearly they have different resistances because they're in parallel. So they've got the same 120 volts across them at A, B, and C, D. They both have 120 volts across them. So delta V AB is equal to delta V CD is 120 volts. All right. The question is, how much power does each bulb use when connected in series across that 120 volts? So if we had a new circuit that looked like this, where you had a bulb here and a bulb here, and they were in series, now what's P1 is question mark and P2 is question mark, right? So I think we have to figure out what the resistance is of these bulbs based on what we know about the power consumption in the first arrangement in parallel. Okay, so I've done some work here. So we're trying to compare the scenario of the parallel arrangement to the series arrangement. And in order to do that, I wanted to find the amount of resistance first so that I can relate that resistance of the bulb, which the resistance of the bulb is not going to change from when it's in the parallel arrangement to when it's in the series arrangement. And I'm talking about the individual bulb. Obviously, the equivalent resistance of the circuit changes, but the resistance of a light bulb is the same itself regardless of what kind of arrangement I put it in. So what I'm going to do is I'm going to use this power equation that lends itself most easily to parallel arrangements here, the delta V squared over R, and I'm going to solve for the resistance of each bulb individually. So I start with a 30 watt bulb. It's got 120 volts across it. It's got 30 watts of power that it's consuming, and I find the resistance of that bulb is 480 when I rearrange and solve for R. Conversely, with bulb 2, it's consuming 60 watts of power with the same 120 volt potential difference across it, which means it's going to have more current going through it to consume more power, so the resistance must be smaller, and in fact it is. The resistance is half of what the first bulb was. So now I'm going to take those two resistors, the 480 and the 240, those two bulbs, and I'm going to put them in series. And I'm going to use a new equation to calculate the amount of power consumed in that arrangement. The new equation I'm going to use is I squared times R. But to find the I have to first figure out what the equivalent resistance is. Well, that's super easy. It's just, these are in series. It's just the 480 bulb plus the 240 bulb. That's 720 ohms of equivalent resistance. And using Ohm's law, I can solve for the current, and it's just the 120 over the 720. And now that I know the current going through here, it's the same current through both bulbs, I can put that current into this equation with the specific bulb resistance, and I can solve for P1 prime and P2 prime as they call it in this problem. So I hope that helps you solve and understand a little bit more about how to apply the power equations in bulb brightness, and we'll do some problems tomorrow in our Zoom meeting to talk about those as well. Okay? Have a good day, guys. See you tomorrow.